So, okay, let's see. Yeah. So, transfer function generator lab exercise. I don't know. This one is like, the cool factor is really high on this one for me. Yeah. The objective, or multiple objectives of this exercise, are to use real-time clock interrupts to provide timing, which is better than the timing that we used before with the wait functions. You can set up a separate, because you know the trouble with our wait functions was that we had a certain number of wait functions, and then we did some other stuff in the loop, right? And so whatever other stuff we did in the loop messed up the timing, right? Unless we timed that out too, which would be a big pain most of the time. So, and they have to be the same every time, every interval. And so we saw things like when we pressed the button to speed button and it was printing, like that slowed it down, right? It's not ideal. It's not really what you want with a timed loop. So there's another way to do it that is preferred, which is you spool off a separate thread that does the timing, that goes through a certain amount of time, and then it sends an interrupt request when that timer dings, you could say. So like every so often, for us it'll be every half millisecond in this lab, it will send an interrupt. And it won't have to worry about what else you're doing because it's in a separate thread. So that's the preferred way to do timing. It's better.
But when we do like that, it means that this is periodic. We cannot, we can predict the time of interrupt.
We can predict it as long as we don't have a certain number of, as long as what we do in the meantime doesn't overfill that time that we give ourselves with the interrupt, we'll be fine. As long as you don't, as long as you go through, do your stuff in your loop, wait for the next interrupt, and then once you get it, then like go do the stuff in your loop. As long as you do that, but the stuff that you do in the loop, your interrupt service routine, as long as that doesn't extend beyond the amount of time you have between interrupts, you're fine. If you take too long to do your calculations, you're going to get interrupts before you're done with that stuff you're doing in the loop. So you still have to be careful. You can't do an infinite number of things, obviously, but you can do them without screwing up the timing, which is so nice. You just don't have to worry about that aspect. So, yeah. So we'll learn how do you do that. So they're interrupts just like the DIO interrupt, with the button that we did before. But this one, the FPGA has essentially like runs this timed loop and just lets you know. Okay. 2, implement an arbitrary transfer function generator. Really cool. We're going to take a transfer function, a third order transfer function, and we're going to make our MyRio between certain analog inputs and certain analog outputs behave like that third order system. So like we're gonna have a transfer function with a certain natural frequency in it, like the second order part of it, and then a certain time constant in the first order part of it, and we're just going to specify it and upload it to the MyRio, and a voltage between that input and that output will appear to have gone through that transfer function, as if there was a dynamic system that was that transfer function in between. So you're emulating a dynamic system. And the method that we're going to use to do this is really cool because you can do an arbitrary system. So like you can do this for any order system, the same functions that will, well, some stuff from the library, some stuff from that you guys will write will work for any of them, which is really cool. You can do a 20th order system and you could emulate it in the MyRio, make it behave that way. Which is cool because that's essentially what a controller does, right? A controller is a transfer function at least in single input, single output control, right? And you do a closed loop. It's just a transfer function that you put in there. So we could make our MyRio into like an arbitrary controller that could do anything the transfer function should be able to do. So it's pretty cool. So looking forward to that functionality. And then also A to D and D to A conversion. We'll talk about. And then there are at least one lecture I want to do this week that's more theory-based, but I want to get us in the lab first, and then to talk about A to D and D to A conversion. Okay, so introduction. Control, measurement, and signal processing systems often include single input, single output dynamic elements that can be described by a linear time invariant differential equation, right? So a lot of the modeling we've done in the system dynamics class and controls say that you put in an input to a system, and that system is described by some transfer function h, and you get an output from that system. So this describes a vast number of systems that we have, and we are interested in emulating that in this lab, I guess. So the dynamic characteristics of the complete system are described through appropriate design of these elements. In this exercise, you will write a general purpose program capable of approximating the performance of any single input, single output linear time invariant system. It's pretty cool. The input and the output will be analog electrical signals. So you could do stuff with like a resonator, you could do all kinds of stuff. We could have fun with it. This is one of those labs that there would be a lot of cool things you could do for the grad students in this class for like doing a cool like extra functionality thing. So like implementing a different transfer function that does something would be fun. Okay. Notice that it is not necessarily a stable system. You could even implement unstable transfer functions in here. You're gonna saturate the output though when it grows. If the output's growing without bound, I mean, it can't really provide a voltage that's infinite, so it'll saturate. But up to that point, you can emulate that. So your program will implement an approximation to a linear differential equation called a difference equation. It has this form. So I want to do a lecture on difference equations and how to derive them for a given differential equation or transfer function. It's not that bad, but there are methods of doing it. And so I should hopefully upload one of those in the next couple days. But this equation is describing the output y at some step n, and it's describing that in its relation through these coefficients, the a naught coefficients and the b naught coefficients, to the output at a previous time step, so the previous time step, and then n previous time steps, all the way back to big N time steps ago, and big M time steps ago in the case of the input. So x in this case is we're using for our input to the system. So x is the input, y is the output. So these are digitized or discrete values of a signal. So this figure is helpful for that. So you think about the input x as having a value at discrete intervals of time, with the interval in between being big T here. And so x takes on a value at 0, takes on a value at 1T, 2T, 3T, etc. And so it's just like any discrete version representation of a signal that you've generated in MATLAB, for instance. We often will do this sort of thing. But in this one, we're thinking of it as being a time domain signal, and the sample period is big T. So the difference equation can represent a single input, single output transfer function by prescribing each output y of n in terms of past outputs and inputs and the present input. So the equation can be written in summation form. So the left-hand side is the sum of a bunch of a's and y's, and on the other side we have the input side, x's are summed up with coefficients b. So we can solve then for the current output, which is y of n, by just subtracting all of the other y terms to the other side of the equation, and that gives us b5. So this is the current output that we should be putting out of our system, given all the past outputs and all of the past and current input. Notice that the most recent output value, y of n, depends on previous values of y and on the previous and current value of input x. The relationship between the constants a and b in the difference equation and the corresponding differential equation are described in section 4.6, which is the theory one that I'll go through. It describes how to get your a's and b's given a certain transfer function or given a certain differential equation. So I'll do a little lecture on that. But suffice it to say that there are straightforward ways of going about that. At the beginning of each BTI, so we have another definition of our BTI in this lecture, or in this exercise. So BTI, once again, is a basic time increment, right, just like it was before. The beginning of each BTI, your interrupt service routine will read the analog to digital converter, ADC, analog to digital converter, to obtain the current input value, compute the current output value, y of n, and apply the current output value to the digital to analog converter, DAC. This process continues until the back arrow is entered on the keypad. So it's going to emulate this transfer function, this dynamic system, by going through and calculating what the current output should be given all the past outputs, given all the past inputs, and then the current input. So it takes in a value, it takes one sample in, and it needs to put one sample out. So that's in any real-time system, if you put in an input value, you want it to be putting out an output value as quickly as possible that corresponds to that, right? So if this is a controller, obviously, that's really important. The shortest amount of time between the measurement and then the commanded, the control effort, the better. So the quicker that you operate, the better. And you don't want to wait for multiple samples, right? Like you don't want to have to wait for like 5 samples and then put in an output value, because it's an analog output. It's continuously whatever it is you're specifying. So you're just not updating it. It's just staying at whatever it was specified before. So you want to do it as quickly as possible. So you take in a sample, you put out a sample. You take in a sample. Essentially, you update your output. You measure your input, you update your output. You measure your input, you update your output. And that's how it operates. And that's how it does it. So, I mean, if you have any sort of digital controller, which most controllers are digital now, this is how they have to work. They have to take an analog signal that comes in, and so when we looked at logic levels in our last week's discussion, we looked at just two values, essentially digitizing to two values, either true or false, right? Now we're going to digitize it to more values than that, and so you have to do that. So decide which level the voltage is. So are we going to approximate it as being 0.1 volts coming in, 0.12 volts coming in, 0.15 volts coming in, whatever it is, and then we have to output something that's digitized as well. But it has to be turned into, because it's going to interact with the real world, an analog signal at that point. So, yeah. The calculation happens digitally, and then the real world application has to happen in analog, because the real world is, at the end of the day, is analog. So you have to end up putting a real continuous voltage out. The real world doesn't ask for voltage just every sample period t. It needs to know voltage all the time. So, yeah. So the input voltage will be provided by a function generator. So we'll use the function generators in there, and we'll in the lab procedure discussion, it'll tell you which functions to generate. You'll put them in, and then you'll take them out and display them on the oscilloscope. And you're going to want to put both the input and the output on the oscilloscope so you can see the input and then the output. So this is going to be really cool. We're going to be able to look at different frequencies, see like the frequency response that's happening too. Like you put in an amplitude at this amplitude, you should be getting out an amplitude that you could predict based on the transfer function, and it should be doing that in the real world too. So it's going to be really cool. This is one of my favorite labs. The input voltage, yeah. So you will use 3 new MyRio features in this experiment. An interrupt timer, like I described to do the timing. The ADC, so the analog to digital converter. So when you're measuring your analog input, you're using the ADC. And then the DAC. So when you're putting an analog output, you have to go through your DAC. The first is described in detail in resource C7 and the other in C6. I will go through those resources at the end of the lecture. But I want to give this is sort of like an overview of the lab, and then we'll go into more detail in these 2 sections. So the first thing is the bi-quad cascade. Although we could implement equation B5 as shown, so we could do this calculation every time. We could just use the previous measurements and the current input and the past outputs and calculate what the current output should be. You can do that. There's an issue that arises though. It's just a numerical issue. There's nothing wrong with it from a mathematical point of view. It's valid. But what happens is that the sensitivity of the output to coefficients leads to numerical inaccuracies as the order of the system n becomes large. So if you have a large order system and you were to calculate what these coefficients b and a are, the sensitivity of the output to those coefficients becomes pretty significant, and you can get rounding errors that'll kind of creep in with this equation. So we don't want to do that if we can avoid it. So we will solve this problem by breaking the nth order system into a series of ns second order systems. This technique is called a bi-quad cascade and is illustrated in figure B10. So we're going to take this nth order system and we're going to break it down into a sequence of second order systems. So you're going to have, if you had like a 10th order system, you could do 5 second order systems, break it down into. And you could think of it as essentially just like factoring the difference equation or factoring the transfer function into several components, and then acting on it with one second order system, and then another second order system, and another second order system. And this, it's not obvious necessarily, but this actually allows us to avoid some of these numerical inaccuracies of computing equation B5. So notice that the output of each second order section, which is called a biquad, is the input to the subsequent section. So it's just a concatenation, one, then the next, then the next, in series. So each biquad implements the same second order difference equation, but with different coefficients. So they all are second order difference equations, but they have different coefficients, different inputs and different outputs, right? So for example, the current output, y of n, from the ith section, so yi of n would be the sum, just like before, of the x I, so the input to that stage, and yi, the output from that stage previously in the two previous steps. So, of course, a first or second order transfer function would require only one biquad. So depending on the value of n, some of the coefficients of at least one biquad may be 0. So sometimes some of our b's and our a's are 0. So we will implement a function to handle any value of n. So pretty cool nth order system. This will work. There are a variety of algorithms for breaking a transfer function into biquadric sections. MATLAB signal processing toolbox contains a function TF to SOS, which is the transfer function to second order sections function for this purpose. You're not going to be required to do those things in this lab. A lot of this is done for you, but it's good to know how to do it if you needed to. So pre-lab preparation. The program consists of a main function and an interrupt service routine running in a separate thread. So just like before when we had to interrupt the main and then we have the interrupt service routine. The ISR is set to execute with a period of half a millisecond, determined by the timer IRQ, and computes the DAC output and from the ADC input by means of a difference equation. So here are some details. The main program. The only task of the main will be the following: set up and enable the timer IRQ interrupt. So just like before when we were initializing the digital input interrupt, we had to set it up in main. We have to do that again, but for the timer IRQ, which is essentially just a different IRQ number, but otherwise very similar. Enter a loop, ending only when we have the backspace pressed from the keypad, so you can use get key for that. Check to see if it's been done. Signal the timer thread to terminate using the IRQ thread ready flag and wait for it to terminate. That is the main program. So the interrupt service routine is the other side. This is where the meat of this lab is in the interrupt service routine. So the interrupt service routine thread implements a dynamic system. The heart of the ISR is a while loop that checks the IRQ thread ready flag set in main to see if the thread should continue. Before the loop begins, initialize the analog input-output and set the analog output to 0 volts. Each time through the loop, get ready for the next interrupt by waiting for the IRQ to assert. So it's waiting for that BTI to start, to the signal for it to start. And then write the time interval to wait between interrupts, so BTI to the IRQ timer write register, and write true to the IRQ timer set time register. Read the analog input to obtain the current input value, x of n. Call a function Cascade, which we'll write as well, to calculate current value of the output, y, by computing all the sections of the biquad cascade. Each biquad cascade section is computed according to equation B6. Send the output voltage to the analog output. and then acknowledge the interrupt. After the loop terminates, save the response to lab6.mat so we can actually see how the system responds. The ISR must allocate storage for variables and arrays associated with a discrete dynamic system, including the length of the BTI in microseconds, the number of biquad sections, NS, and the system constants, A and B, for the biquad sections. The dynamic system corresponding to the collection of biquad sections can be conveniently referred to and manipulated by first defining a structure to contain the coefficients and previous values of input and output for a single biquad section. We might define a biquad structure as follows. So they're all going to be second order. They're all going to be biquad, so we only need A's 0 through 2, and then outputs Y1 and Y2, and then Y0, I suppose, would be the thing we're calculating in the biquad, the thing that it returns. This definition should be placed just before the prototype section of your program. Then, a specific dynamic system can be defined as an array of those biquad structures. So this is one biquad structure, but remember we're going to have a cascade of them representing a system. So a specific dynamic system can be defined as an array of these biquad structures, each array element corresponding to an individual biquad section. So this would be how to do that. Number of sections, in our case, is going to be 2, because we're going to do a third order system. Timeout value is going to be 500. It's in microseconds, so we want our BTI to be 0.5 milliseconds. So we say timeout value for the timer interrupt thread is going to be, 500 microseconds, or 0.5 milliseconds, which corresponds to a sample frequency of 2,000 hertz. And then you can specify this biquad filter. So my filter is, we specify one biquad and then specify another biquad. So that would define our third order system. The system description can be placed within the ISR near its beginning. The first 2 lines establish the number of biquad sections and the length of time in BTI of the BTI in microseconds. Finally, my filter, so this definition here, is the name of an array of biquad structures being initialized. So this is the initialization. For testing purposes, the initialized constants in the example above correspond to a system of 2 biquad sections, NS equals 2, encoding a unity gain low-pass filter with sampling frequency 2,000 hertz. Derived using Tustin's method, they correspond to a third-order continuous system having a complex pair of poles with natural frequency 40 hertz and damping ratio 0.5. The remaining real pole is at 40 hertz as well. So that's the system that we've implemented there. So there's a transfer function that's already ready to copy and paste in. But yeah, what's your question?
So for the biquad, my filter, are those values, are those the input coefficients?
So these correspond to these guys. So B0, so the first one, like 1, so B0 is 1, B1 is 0.999, yeah. B2 is 0. A0, so these are all of the coefficients that define the difference equation, B6. So what we've done is we've defined 2 biquad sections, right? So this is the first one is the first 2 lines here, and the second one is in the next 2. And these 2 biquad sections correspond to the biquad transfer functions turned into difference equations. So in correspondence with B6, which is right here, with this equation. Does that make sense?
Yeah.
Okay, cool.
Like two, one is for output, one is for input.
So the biquad definition that we've given here, it's going to be used to take in an input and then give an output for that. That corresponds to this difference equation. So we'll talk a little bit more about how to actually use the biquad struct, the myFilter array. So yeah, so we'll revisit it in terms of how to actually use it, but this is how to define it. So we define it in this way. We're gonna have to use it to compute essentially B6, right? So we're gonna have to write B6 into a function, and that's what our cascade function is going to be. So we have this definition here of what the biquad is, and we're going to use that biquad definition in our cascade function. Okay, so we'll get to that. So.
Also, is like IRQ timer write and IRQ timer set, are those like in the header files, or those
Yeah.
functions? Or?
Those are, so we'll get into the details of how to do this when we look at the resource section on so I have a resource section on timer IRQ, and these two will show up, but essentially they're constants that are shown up, that show up, and I show you how to write to them. So yeah. So this this capitalized thing, IRQ timer write, is actually a constant defined in the header files. Writing to the register that corresponds to it will be shown in the appendix. So you'll be able to see how to write to that register. So we'll fill that in a little bit in the appendix. Okay, pointers. This is something that I haven't required in a lot of the labs that you use pointers, and so you can get away with using array indices a lot of times, but they're a lot less efficient. So, since this is something that's going to happen pretty high rate, we don't have time. Like, this interrupt service routine has to finish all its calculations in less than half a millisecond. So, you have to be very efficient with how you calculate things. The pointers are a lot faster. So, that's what this crazy about pointers section is telling you. The most challenging part of this task is the calculation of the current output value, y of n. Use of pointers makes the calculation both straightforward and efficient. Don't be tempted to use array indices instead of pointers in this code, because that will be much too slow, and your timing will essentially be way off if you miss if you aren't finished with your calculation by the time the next interrupt comes, then you're never going to catch up. So the cascade function. It implements the complete dynamic system by passing the measured input through the string of biquad sections. The ISR must pass to Cascade the value of the current input x of n measured by the ADC. The number of biquad sections ns, the array of biquad structures containing the coefficients and history of variables xi and yi for all sections, they all have to be passed to Cascade. It might have a prototype that looks like this. So here's an example. You would want to have what is the input, what's the biquad array that was defined above, so this guy, right, myFilter in this case. NS, number of segments, the minimum output and the maximum output. And those are there because we're going to want to do our own saturation and clipping in the function, because we actually have hardware limitations, and we want to make sure that we don't tell it to do more than it can do. So we're going to limit that at the software level. In the above example, my filter would be passed through FA. The value returned by Cascade is the current value of the system output y of n. So your Cascade function is essentially your function that computes y of n. So like from equation B6, right? Okay. Some advice on coding Cascade. An efficient way to code Cascade is to allocate a pointer f in Cascade that will be used to point to elements of the array of biquad structures. Begin the function by equating the pointer to the first element in the array, i.e. the first biquad. So say f equals fa. Variables inside the biquad structure are accessed by using the pointer name, for example, f, and then remember what this notation is, this right arrow notation is. Say it looks up, it dereferences the pointer, and then it looks inside that structure for the member of the structure associated with A naught in this case, or B naught in this case. So it's like shorthand notation for dereferencing F and then asking it for the A naught structure element member. It's typed as a minus sign followed immediately by a right arrow. I don't actually know what that symbol is called. A greater than symbol. Then loop ns times. So do that for, so essentially what you're doing is you're calculating the output of a biquad in one loop. And then you're going to use that output as the input to the next biquad. So you're going to iterate your pointer and then look for all the A's and B's again. Do it again. So loop through ns times, the number of biquads. So in our case, it's only going to be 2, but you want to write your code so that it could handle n. And in fact, this is a really useful thing. So like writing this well this time, if you guys want to, like for a senior design project or for anything else, implement a controller or some other emulation if you wanted to, instead of just using it as a controller, you could use it as something else. But controller is a really good example. Using MyRio as a controller, design your controller in MATLAB, have it dump out what the coefficients are, your A's and your B's, your biquad coefficients are, and then you can immediately implement that controller after you design it in, so like PID controller or whatever it is, you can immediately implement it on a MyRio by just using this. So I would make sure that you write it generally, like I'm requesting in here, and not just for ns equals 2. You want to be able to write it for any number so that it loops through them all. You might as well. If you're going to do it for 2, you might as well do it for n. So, okay, good. Within the loop, so loop to cycle through each of the biquad sections. At the beginning of each loop, the output value y naught of the previous biquad must be passed to the input value, which is f x naught of the current biquad. So the output of the last one is the input, the current input for the next one. Within the loop, coding the output value y naught might look like this. So y naught equals, and I wrote part of it, right? Etc. Right? So I left a hanging plus sign here. You got to put more in here, right? Yeah. And then you're going to divide by a naught. So this is essentially equation B6, right? So I started B6 for you. Or B7? B6? What is it? I wrote B6 there.
B6 is that n equal to 2.
Yeah, B6.
But for this one, it is the advantage of assigning as a pointer, so we can access to each element the structure of this.
Yeah, so that's one of the advantages. Also, it's just faster than using array indices to use a pointer to access each value. So yeah. So you could use a pointer to the structure, or you could use another array index and then ask for the array index.
Like that wrong.
But it's slower, yeah.
Because when one index is wrong, the other will be wrong because we are adding up the index somehow. But this one is just call out names in that pointer, so clear.
It's also, yeah, it is nice too because you
Yeah.
call out the names, right? So like whenever you're looking for your B naught,
Yeah.
you write F B naught. You don't have to be
This
like,
is
okay, this is
inside,
the
yeah.
first one, the second one. Yeah, totally.
Cool.
But yeah, even the it's like F, your current F is a pointer to an array value, which is a struct, right? So when you increment the pointer F, it goes on to the next array, it points to the next element of the array. So you could do that using an array index, but it's much faster to use a pointer to do it. So, and it does notationally look nice too.
Yeah. For this one, we have the advantage of rearranging the number the way we want, and it will always go to that number.
That's
And
true.
You don't have to do indexing.
Right. You don't have to know that B
Yeah.
naught was first.
Then
and-
when
yeah.
or something like this.
Yeah. So you could have defined, instead of defining a biquad struct, we could have defined a biquad array, but then you'd have to remember which one was which.
Yeah.
Yeah. Is B0 the first element? Which element is A2? So it's nice when you write stuff in a struct so you can access it from a name, from the member name, which is nice.
Now, previous lab we used a part of it also. You explained it also in the.
Yeah, so using this operator to access an element. Yeah, it's a nice little notation. It's pretty useful. And well, as with everything that you program, you could do this a lot of ways. This is a good way. There are probably other good ways, and then there are bad ways. So each time, so each time through the loop, after the output value has been computed, the previous values x and y must be updated so that they will be correct the next time step. For example, you want to assign to the x2 member of the array that f is pointing to, or of the struct that f is currently pointing to, f going to x1. So you have to update them, right? Because remember, x1 corresponds to the output, or sorry, the input from last time. And so we correspond the input, we assign the input from this time to the next up last time input. So we have to, we're passing these through, right? We're passing them from x0 to x1 to x2, and then that one goes away. We only have to remember 3 time steps for this system. If it was higher order, we'd have to remember more. At the end of the loop, the pointer f is incremented to advance to the next biquad in the array. One more point. If the digital to analog converter is given a value beyond its range, -10 to 10, it will saturate its output value appropriately. However, our difference equation, B6, depends on previous values of the output, but doesn't saturate. To correct this disparity, Cascade should saturate the output Y naught of the final biquad before it is saved to the next iteration. And that's because so you could have your biquad, you could have your your DAC, you could say, okay, put out 20 volts. Well, it's not going to put out 20 volts. It only put out plus 10 volts, the highest. So you can say 20, but it's not going to put out 20. But, so you might say, well, what's the harm? You can say it, it's just going to put out 10 anyways. And the harm is that we're going to use our previous value of that output in the next calculation of the output. And if we're actually saturating, we want it to be reflected in our algorithm. We want the next point to be calculated based on something that was true in the past, in the point before, and not on something that wasn't true. So we saturate it in software so that we know what really happened, and not go off and like say, oh, okay, now the output was 20 last time, let's make it 22 this time. Well, it couldn't have do 20 in the first place, so you've just been putting out 10 every time. So the saturation effect is mitigated a little bit by doing the saturation in software too. So you're reflecting what's happening out there. Okay, so you can do the saturation in a lot of ways, but this way is an efficient way to do it. So you may not. I don't know if I told you that you could do this. I think I might have mentioned it. Remember when we talked about macros real early on? We talked about how most of the time they're used to like replace a constant somewhere, but you can actually like write them like a function if you want to. And you can have it overwrite something based on some function, some logic. And you often will write on one line. I wrote it on 2 lines because it overflowed my box and it was way over here. So in order to continue a define macro on the next line, you use the slash. And it's a useful idiom. You can just keep going to the next line. So you can write it looks just like a function, but it's actually a macro that'll be run in pre-processing before it gets compiled. So pretty nice. So that would be one way to do it. It's a pretty nice way to do it. It's fast. Yeah.
So for this, is it just like looking at every single x and seeing if it's within -10, 10?
Yes.
If it is smaller than -10, it must be -10. And if it is bigger than 10, it must be 10. Is that what it means?
Yeah. So if it's bigger than 10,
10.
it has to be 10.
Yeah.
If it's smaller than -10, it has to be -10. So this will go through and it will do this logic on each value. So it'll saturate the value based on this code. So it's a pretty nice little way to do it. There are other ways you can do it. You could try and just see how long the other ways take if you wanted to like write a function. You could write the function that's not as a macro. It will be a little bit slower, but it might be a little bit. You can do like error checks in it if you wanted to and stuff, and you can debug it easier. When you use the macros, it's really hard to debug with them. So like if you wrote your macro incorrectly, which would be hard to do considering it gave you the code, but if you did, then somehow, challenge accepted. If you found a way, it's hard to debug these. So like you can't follow it into the saturate and see it go through because it's not a compilably. Your debugger depends on it to being a function that it can follow in, but the macros can't be. So there is that. So it's like you got to be a little careful with these. You won't see a bug. Like if you run the debugger, like it won't catch this bug. The compiler. Right, yeah, like you wouldn't be able to see like, oh, when it comes in as 11, instead of going to 10, it goes to 1,000. Like you wouldn't be able to see that in like by going through and stepping through your debugger. So it use with caution, but for something simple like this, and you can debug this logic separately as a function and then write it as a macro if you want. Use with caution, good for simple little things. Pass appropriate values of the xmin and xmax parameters to Cascade. Then, for the last biquad, immediately after y naught is computed, so your final output, so now you're ready to write it to your analog output, saturate its value. So if it says 11, coerce it to 10. So just call it with this function.
Like a function, yeah, we call it.
It's just like a function.
We hand in this argument, y naught, y min, y max, and then we get our result.
Yep. It'll coerce it either to y max or to y min. But if you try to follow it in the debugger in step in to saturate it, won't let you. So, there's that. Lab procedure. A good strategy to follow in writing the program is to first implement and debug everything except the calculation of the biquad cascade. I mean, the biquad cascade is the heart of what we're doing, right? We're implementing the biquad cascade. But you can get everything to work in this when it's actually really easy to see if you measure an input and instead of putting it through biquad, if you just write that immediately to the output, then you can set up your timer without having to do the biquad cascade. You can set up everything. You do all the timing. You can do all your main stuff. Set all of that up. The IRQ stuff. Do all that first, and by just taking in whatever it inputs and putting it to the output. So you're doing all the stuff you need: analog input, analog output, timer, interrupt. Except instead of calculating through the biquad cascade, you're just taking whatever came in and putting it back out. So you're trying to simulate a wire. You're trying to emulate a wire. So whatever voltages come in, it should go out. And it's really interesting to do this because you could look at it on the oscilloscope, and you can look at what the difference of time is. So you can look and say, what's the difference between? So it should look like the same wave. So if you're putting in a sine wave on the input, and you should be seeing a sine wave on the output. It should have the same amplitude as long as you're not saturating, and there's going to be a time shift because you're not going to be an actual wire. There's going to be a time lag between, because it has to take in the measurement and then it has to write it back out. So it has to do the A to D conversion, and then it has to do the D to A conversion. So that takes time. I mean, this is a pretty fast little machine, but it will take some amount of time. So you should be able to zoom in on the oscilloscope and see that there is a little bit of time delay there. And that should correspond approximately to your BTI, your half millisecond. So it should be about a half millisecond. I want you to try to explore how, try to describe how that might not be exact, or like what, if it isn't exactly a half millisecond, I want you to kind of explain why that might be. It might be that the measurement's so close that it's hard to tell that there's much difference going on. But I think it'll be interesting to see. So explore, what is the difference? It should be around a half millisecond. And you should be able to describe why it's any different if it is. Or I want you to think about it. Come up with some theories. So when you have debugged those portions of the program, augment the code above with the call to Cascade. So then, instead of just putting out whatever you got in, actually change it to what the dynamic system should be putting out based on what's coming in. So then implement the Cascade. So I would do everything except for Cascade first. Like that would be like number one, like write it all. And then even write your Cascade function, but just have Cascade just return whatever it's given. I mean, you could leave Cascade out altogether like I did here. This is just completely just saying, whatever I got the voltage of the A to D converter in, so read it, and then turn around and write that same value to the output. So that's one way to go. You could even pass it through Cascade, make sure all that machinery is working, but just have Cascade return whatever you give it. Okay. Does it work? The low-pass digital filter described above was derived using Tustin's method, which I'll describe a little bit in one of the theory lectures I'll do this week. But it's a method to go from a transfer function to a discretized system with a difference equation. So this is the transfer function that was implemented in the filter that was given above. So it's third order. It's got 3 poles. So one second order pair of conjugate pair of poles, and then one real pole. And this system belongs to the class of filters called a Butterworth filter. They're signal processing filters designed to have the flattest possible frequency response in the passband. So if you look at the Bode plot of this, so look at the frequency response function, it's going to be very flat up until the natural frequency, and then it's going to drop off pretty quickly. So it's a low-pass filter. It's going to pass the low frequencies. So this is frequency, and then this is the magnitude of the frequency response function. So it's going to look like that. This is the dynamic system. So we expect that at low frequencies, it's going to just pass through the signal. So it'll look just like our original, like, take an input, write an output. It'll look like that at low frequencies. But then as we increase the frequency of the input, if we like had a sinusoid that we're increasing the frequency of, when it gets out here, this filter that we're emulating is going to have a smaller and smaller output. So as you increase that frequency, the input will stay the same on the oscilloscope, but the output's going to get smaller and smaller. So it's pretty cool. It's a pretty cool system. It's a nice filter, and so this is a filter you could use just for, like for instance, if you had a system that was a noisy system, say, and you wanted to make a measurement that filtered out the high frequency noise, you could use a Butterworth filter to do that. And so this is a Butterworth filter that would do that. It would filter out high frequency noise.
Only the low one?
Takes only the low frequency stuff. So if you put in a signal that had a lot of low frequency stuff that you care about and a lot of high frequency stuff that you don't care about, it would look really messy. But you would clean it right up if you ran it through a Butterworth filter like this. It would filter out the high frequency stuff and make your low frequency stuff nice and clean. So that's the type of thing that this digital filter is doing for you. It's pretty cool. So I mean, you can think of it as a filter, or, you know, alternatively, you could think of it as being another type of dynamic system that you're representing here. It could represent any electron. I mean, it's already electronic, right? So just if you're like, okay, this thing can represent any circuit pretty easily. So like you could draw up a circuit, find its transfer function, and you could build the circuit in like, analog discrete things like elements, build it, put in an input value, measure the output value, and then you could take that same input value and run it through the MyRio, and then it'll give you essentially the same output value, or very close to the same output value that the real circuit does. One nice thing about having it be digital is you could decide you want your system to behave like a different system, like suddenly like add a capacitor in there, boom, or double the capacitance of something in your circuit. You could immediately change, without having to change any hardware, how that system is behaving, whereas you couldn't do that in the analog case. You'd have to build a new circuit or change the circuit. So, yeah, one of the many advantages of doing something digitally. So, step response. So, using the oscilloscope in DC coupled mode, observe the step response of a system by applying a low frequency square wave, for example at 8 Hertz, with an amplitude of 5 volts as the input with a function generator. Save the input and output of Cascade in 500-point buffers. After the timer loop ends, save the buffer to lab6.mat and transfer the data to MATLAB. Plot and compare the measured step response to the theoretical response of the corresponding continuous system, and explain how this works. So MATLAB's LSIM is a good choice for generating the response to the continuous system. So you're going to have a theoretical step response. So it's this why is square wave? I mean, why do we repeat it over and over again? We're looking for the transient response, the step response. Why do a square wave to find the step response? Well, it's because it happens over and over again. If we wait long enough before we do the next square wave, though, it's as if it was a totally independent step input. So it's like we're repeatedly doing a step input. So for those of you who went through the mechatronics lab, we did something like this in the mechatronics lab. But when you put in a square wave, it's like putting in a bunch of step inputs that are spaced out a certain amount, right? So, like for instance, this first one, you're going to see a response like this, and then you're going to see a decay back down to 0, and then you're going to see another response like that. So the input is the square input, and then the output is this. So there might be a little bit of oscillation. I don't want to say for sure because the second order system is in there, right? 0.5 as the damping, so there could be a little bit of oscillation, but there wouldn't be a ton of oscillation. So we're going to look at that. We're going to measure 500 points, and if our sample rate is, so if we take a point every 0.5 milliseconds and we multiply that by 500, then we'll be taking, yeah. Uh, 0.0005 times 500, quarter of a second. So for a quarter of a second, 8 Hertz is 0.1625, or whatever it is. Yeah, that is so you'll essentially see a full period of this happen. So that's why 500 points. So then you'll be able to reconstruct, so here's what the actual response is. And then you can simulate it using, I would recommend LSIM in MATLAB from this transfer function B7. So if you're unfamiliar with using MATLAB to do simulations of these sorts of systems, then this transfer function could be input in there using, I would recommend it's always a little tough to decide if you're going to go with ZPK, which lets you specify the zeros, the poles, and the gain. I think that I would prefer TF in this case. And then you can give it the polynomial coefficients. You do have to do one of two things. You either have to multiply this all out so that you get coefficients for one polynomial, some 1/3 order polynomial in the denominator, or you can define two separate ones, which is the cheating way that I would use, to define two separate ones and multiply them together. MATLAB lets you just multiply them together. So I would just create two separate polynomial transfer functions with TF, and then I'd multiply them together to generate this one. And that is the one that I would do LSIM on. And then I would generate like a square wave and put the square wave in, see what it would look like. And I would generate the, also we're going to have you do a sinusoid as well. So you should see what the response should look like for each one in theory, and we can match that up to the experiment. And they should match up pretty well. So that's a good thing. Like, so sometimes I think when you do a lab, you're like, I don't know if this is really going to match up that well. Like, this one should. It should get really pretty dang close. Okay. Frequency response. Again, using the oscilloscope, this time AC coupled, observe the frequency response by altering the frequency of a 5-volt input sine wave. So not a square wave in this case, a sine wave. Record by just like writing down. You don't have to like use any like digital electronics to record it. You can just write it down. That's why I wrote write down. Because I think that sometimes in this class it's hard to tell. So write down the amplitude and phase of the output relative to the input sine wave at the following frequencies. So 5, 10, 40, 60, 100, 140, 200 hertz. So at those different frequencies, looking up here, our natural frequency is, so like 240 radians per second. But if you divide that by 2 pi, of course, it's 40 hertz, right? So the natural frequency is about here. So we're going to do some points below, which we expect to come out amplitude and phase should be about the same. So it should pretty much just pass through these things. Up here, we're expecting to see the amplitude lower on the output than on the input. So we should see the amplitude should be decreasing as you increase the frequency. And we should see a phase shift start to get exacerbated in this as well, the phase between the two. So the phase lag should get worse and worse at the higher frequencies.
From the input to the output.
From the input to the output, yeah. So the input will lead the output more and more as you go to these higher frequencies. Yeah. Given the input amplitude, compute the transfer function magnitude in dB at each frequency. So we're essentially measuring the magnitude, and you do need to write down the amplitude and the phase. So I'm only having you in this part compute the magnitude of the frequency response function, which is essentially just going to be whatever the output amplitude is divided by the input amplitude, right? That should be the ratio. So the output amplitude over the input amplitude should be this magnitude of the frequency response function, which I did use H for, but I should have used T, because T is the transfer function we've got. So T of j omega, the magnitude of the frequency response function. So then in MATLAB, plot the theoretical Bode plot, so the magnitude and phase versus frequency. But do the phase, or do the phase in degree, or do the frequency in hertz rather than typical Bode plot, which would be typically in radians per second. Do it in hertz because we're using all these hertz values, and so it's good to have it in the same unit. And then plot the corresponding measured data as discrete symbols on top of theoretical frequency response. So this is what a theory one might look like, and then we're gonna be taking these measurements at these different frequencies, and we should plot those on top and see what they look like. And it should be pretty good. It should be pretty close. And the phase as well, you measured the phase as well, so we should also have a theoretical phase, and I'm going to move that axis up. And we should see something that goes to like negative 270. And then you can put your measured phases on that too. Okay. That's like the lab. Nothing to it. Okay, are there any questions before I dig a little deeper into how to do the timer interrupt and how to do analog input and output?
One break.
Oh, we'll have a break, but
Yeah, I can't think of anything right now.
okay. Cool.